As we move on to the next section in 8.1, I want you to make sure that you look at page 178, all right, and look over the planetary data. It might even be something that you want to put into your index card for formulas and keep that going. The next thing that we're going to talk about is universal gravitation. All right? In the section about universal gravitation, they come back to the component of what we were saying right before when we were talking about these elliptical orbits, is that because orbiting objects move faster when closer to the sun, the force varies inversely with the square of the distance. So putting it into a relationship, that the force between the two objects is proportional to, or inversely proportional to, the distance they are apart, or the radius squared. So not only as it gets further away, the force gets less, but it's exponentially less as we move away. Then we come to the universal force of gravity and its formula. What this formula states here is that when we have two objects of mass at a particular distance, in this formula is represented as d squared, sometimes it's r squared, and all multiplied by the universal constant of g, which we will use all the time, just like how we use pi to do math with circles. And that is the relationship to calculate the force of gravity between any two objects. So any two objects in the universe have a force between them. You and the chair you might be sitting on, if we were in class, a force between me and you, the force between one chair to the next. So all objects have a force of gravity. However, we normally don't feel that excess of gravity because the mass that we are focused on is the Earth, and the force between us and the Earth is so great because the mass of the Earth is really, really big. So what I want to focus on is the relationship between what we learned in chapters previously, that the force or force of weight right here, or Newton's second law, was F equals ma. Remember that that is the relationship between the two. And if we compare these two equations, they should have equivalency. So what we're going to do right now is show you that comparison of what they tried to do in the video, that I'm going to try to do in this video, and what they tried to do in the textbook. So the first thing I want to focus on is Newton's second law, which we know is F equals ma. Then over here we have universal gravitation that we discussed is the force between any two objects is equal to the gravitational constant, the mass of object 1, the mass of object 2, all over the distance they are apart. And we'll just talk about that in the radius. So if we're trying to put that together, if we're using this formula and we're not just taking an acceleration like we know what's for gravity, since the objects are in motion in a circular path or a motion that is angular, we can then change this formula into F equals m centripetal acceleration. And from last chapter, we learned that centripetal acceleration is equal to the velocity squared over r. Well, if we're talking about an elliptical or a circular path, we can use the circular distance because that is what we're going to be focusing on here. And remember that we talked about the velocity centripetal is equal to the distance around the circle, which was 2 pi r, over the period that it was moving. So if we take this and sub it in, we get 2 pi r over t. Since that is representing v, we have to square that all over r. So when we do that, we will get 4 pi squared r squared over t all over r. So when we do that, what we're going to do, t squared, we're going to cancel out one of the r's. And so we're going to get that centripetal acceleration is equal to 4 pi squared r all over t squared. And then when we sub that in, since we have force equals mass times acceleration, we just will have this formula, F equals mass times 4 pi squared r over t squared. Well, when we were dealing with these objects, remember that we were understanding that it was the mass of the object on the planetary body. In most of these cases, we're going to be talking about planets moving about the sun. So this would be the mass of a planet. When we go back over here and we talk about this formula, we'll talk about gravitational constant, the mass of a planet, and since we're orbiting around the sun, we're going to be talking about the sun and the distances they are apart. So when we try to put this into this formula and compare them, let's set them equal to each other. So we have the mass of a planet, 4 pi squared r all over t squared, and we set that equal to g, mass of the planet, mass of the sun, all over r squared. Well, the masses of the planets disappear because they cancel out. It's the same on both sides. And what we were trying to do is calculate a period, so we want to get this period to the top. So we do that by multiplying both sides by t squared, and that will cancel out our t squareds. But if we want to get this all by itself, we want to multiply both sides by r squared. That will cancel out this. And then we want to divide both sides by g. That cancels out this g. And the mass of the sun, g, mass of the sun. That cancels out. And just to clean this up a little bit, what we have here is we have 4 pi squared. We have 1r, and we have r squared over here, so now that's r cubed, all over gravitational constant, mass of the sun, equals t squared. And if we want to simplify it down just one bit further, remember, take the square root of both sides, and it's best bet to put your parentheses around this, parentheses around this, parentheses around the whole thing, and then square root it, and then we will get down to the period. That's what we are trying to basically explain, the connection between Kepler's laws and Newton's law of universal gravitation.